Okay, let's have a look at torsion here. What torsion is the a twist about the long axis of a shaft, generally. So for instance, in this setup here, we have a motor with a drive shaft that goes into the pump. The drive shaft coming out of the motor here would be under torsion. Okay, here's another setup where we got a motor with a shaft. So right in there where that pointer is, right in there, we'd have torsion on that shaft coming out of the motor as it drives this device down below. I think that's another pump. So this shaft right there coming out of the motor, that'll have torsion in it. It'll twist about its center axis. Okay. So there's torsion being applied to a couple of shafts. Torsion corresponds to the right-hand rule. So that counterclockwise torsion there would be positive, the one I have circled in yellow. This other would be negative. Now, torsion is very much related to shear. So if you think of a shaft as being a series of coins stacked up and then turned sideways, let's draw a horizontal line along the center of the coins. Let's apply a torsion shown there in black. What'll happen is each coin will, let's take these coins and glue them together with an elastic glue that will allow each coin to move a little bit with the one next to it. When we apply this torsion, what's going to happen to this horizontal line is it'll kind of turn into a diagonal line as each one of those coins twists a little bit. What's happening is one coin is twisting with respect to the previous one, so you get shears that build up between the coins. That's what would happen there. Okay. So torsion is very much related to shear in the shaft. Now the nature of that relationship there is looking right here. First, let's define a couple of things. Rho is the distance from the center of a shaft to some point in the shaft. Rho max would actually be the radius of the shaft then. So if we have these shears building up on these little elements in the shaft, and we look at that distance rho of each of these elements from the center, the shear would be rho. Excuse me, the moment, so we have the shear here acting on each of these elements. To relate that to the torsion, what we would do, we would take the shear times the area over which it acts. So tau, which would be a shear stress, times the area over which it acts. So stress times area would get you a little force going that direction. If you then multiply it by the distance that little element is, that little dA element is from the center of the shaft, you'd get a moment arm times a force. If you add up the effects of the shears on all the little elements in the shaft with an integral here, you'll get the total moment about the center of the shaft, which is the torsion. Okay, so there's that relationship there between the torsion and the shear. All right, now let's look at a shaft. Let's take this horizontal line here from A to B before the shaft is loaded. Let's start with that horizontal line. And then let's twist the shaft a little bit with a torsion. What's going to happen there is B is going to roll up to B prime. Okay. Now that arc length from B to B prime will be the angle in radians times the radius. Okay. And this phi angle in here, as B rolls up to B prime, that's the angle of twist in the shaft. Okay. And so that arc length again is the angle in radians, phi, times the radius, r. Now, if we look at that arc length from E to E prime, that distance will be rho times phi. Rho is the distance from the center of the shaft C to E. So notice that for a given angle of twist, phi here, this arc length will vary depending on how far out you are on the shaft. The further out you go, the longer the arc length. So now what we could do is we could take the skin off the shaft, the outer layer, let's say, and lay it flat and look at what's happening as that point rolls up from B prime up, or excuse me, from B to B prime. Okay, so what's going on here is we're going to have the length of the shaft right there. And then we'll have that distance from B to B prime. Okay. Now that's an arc length, but now we're laying it out flat on the table here as we take that layer off the outer edge of the shaft. So what's going to happen is we're going to end up with a right triangle here. Our original line went from A to B. Now it's going from A to B prime. Okay, there's A to B and A to B prime. And then we would have the edge of the shaft there going from B to B prime. Okay. So what we would have then there would be R theta, which is that arc length, and that's our delta. Now, if we look at a little square that we could draw right in here at B, when that rolls up, when this B rolls up to B prime, that square is going to turn into a rhombus. Okay, and there'll be a little angle in there. So what we have here, if you look at what's happening to this little square element, is we have shear strain going on there. The square element is now turning into a rhombus. If you look at that little angle there in the corner, that would be the shear strain. Okay, the angle right there in the corner, that's equivalent to that angle B prime AB. So the shear strain is expressed right here. Okay. Now notice if you're looking not at B prime AB, but we're looking instead at E prime AE. Okay. So now we're inside the shaft, we're not on the outer layer. We're going to have those same sort of relationships, except that this angle here will not be as great. Okay, this shear strain angle will be less. Okay, because E to E prime isn't as big a delta as B to B prime, so that little shear angle there will be less, and so the shear strain here will be less. Okay, so the shear strain is maximized as you get out to the edge of the shaft, and there's a linear relationship between how far out you are from the center of the shaft and that shear strain. So boxed in here in red, what we have is the fact that the shear strain divided by the distance rho from the center of the shaft is a constant. The further out you get from the center, the greater the shear strain, and it's a linear relationship. So the shear strain gamma over rho is a constant. Okay. So for a given twist angle theta, we have different shear strains that increase as we get further and further out from the center of the shaft. As we go that way, those shear strains get bigger. Okay. So the maximum shear strain occurs on the very edge of the shaft. Now here's an example of that. Here's a shaft, a foam shaft that can be pretty easily twisted. There's a little element on there. When you twist the shaft, that square element now turns into a rhombus. So you can see that shear strain effect when you twist that shaft. Okay, so we can develop a couple of equations here that we can use. When we work through these, we want to realize that the shear strain gamma over rho is a constant. Okay. And within the proportional limit, G is tau over gamma. So tau, the shear stress, is G times gamma. So if we take this relationship here, gamma over rho, and just multiply it by G, we'd get tau over rho. So the tau is the shear stress. So not only is the shear strain over rho a constant, the shear stress over rho is a constant also. Okay. Now, underlined in red here, I have the basic torsional relationship. It's the integral of rho tau dA. Now, I can work with this algebraically. What I could do is I can just put a term of rho over rho in there. right there. I've boxed it in red. I'm going to erase it so you can see the tau, but there's that term that I've added to that integral of just rho over rho. Okay, now that's just 1. It doesn't change the value of this thing. But I can now rearrange it algebraically and get tau rho squared dA over rho. See, that tau over rho is a constant. I can pull it out of the integral. And what I'm left with then is the integral, as I've underlined here again in red, of rho squared dA. Now what that is, if you remember back to statics, the integral of a distance squared times the area to the distance from a given axis is the moment of inertia. So the torsion is the shear stress tau times the moment of inertia. It's a polar moment of inertia because we're measuring out from the center of the shaft in a radial sort of way. So it gets a little subscript of P on it now. So that's the shear stress times I sub P divided by rho. So there's the torsion. If I solve that for the shear stress, I get the torsion times rho over I. Okay. And then what I can do, as I've boxed it in red, I can find tau max, which is really what I'd be interested in if I'm designing the shaft, would be the maximum shear stress. That's the torsion times the radius r over I, and then that p is a subscript to show it's a polar moment of inertia. So the maximum shear stress in a shaft is the torsion times the radius divided by I. Okay. Now, once again, what we can also do here is look at this idea of shear strain being r phi over L. We can solve that for phi, the angle of twist, and that's the shear strain gamma times L over R. I can do the same sort of thing I did over here, but this time I can do it with G. I can introduce a term of G over G into that relationship, and then substitute the shear stress is G times gamma, because I've got on the top of this fraction, I've got G and gamma multiplied together. I can substitute tau in for that. And I can get an expression for the angle of twist. It's the shear stress times the length divided by R divided by G. Now I really want to know what the angle of twist is here in relation to the torsion. So the shear stress is the torsion times R divided by I. So I can substitute that into this expression that I've boxed in. And I'll get a pretty, a lot of terms on this one, but I've got R over R, so I can cancel those and end up with this relationship down here at the bottom that I've boxed in, that the angle of twist phi on a shaft, which is right up there on the shaft wall, okay, or excuse me, on the cross section of the shaft, I should say. So there I've got phi. That's going to equal the torsion times the length. So the greater the torsion, the more that angle will be. The longer the shaft, the more the shaft will wrap up. So that'll increase the angle. And then on the bottom of the fraction, I'll have the moment of inertia, which will resist that twisting action, and G, which is the shear modulus. The higher the G, the less the shaft will twist. Okay. So the angle of twist phi is the torsion times the length divided by the moment of inertia divided by G. Okay. Now these are the two fundamental relationships that we use when we're working with shafts. So I've boxed them in. The maximum shear is TR over I, and the twist angle is TL over IG. Now I have these labeled here, angular, because that's an angular relationship for twist angle. Notice the similarity that that has with the linear relationship here that I'm circling right now, that we've already studied. Delta is analogous to phi. Delta is a linear deformation. Phi is an angular deformation. Here I have torsion. Here I have load. They're analogous to each other. The lengths of the members relate to each other. So I've got L and L. Then I've got the moment of inertia for a shaft versus the area for something that's under axial loading. And then I've got the modulus of elasticity E versus the shear modulus G. So these are analogous relationships. Phi is TL over IG for angular relationships, torsion, and delta is PL over AE for linear relationships, axial loads. Okay. So with torsion, we're going to work with the tau max formula and the phi formula. Okay, just a derivation here of the moment of inertia. What you would do there to find a moment of inertia is you would break up a shaft into a series of rings that are a distance rho out from the center. Your moment of inertia then will be the integral of rho squared dA. Now to get the area of this ring, I'm going to take its length, which is the circumference of its circle. It's 2 pi times whatever that rho distance is. And then I'll multiply that times the thickness, which is d rho. So I've got the integral of rho squared 2 pi rho d rho. The 2 pi is a constant. It can come outside of the integral. I integrate rho cubed d rho. I get rho to the 4 over 4 times 2 pi. My limits are going to go from 0 to the outer radius, so I can substitute r in for rho. So the moment of inertia is 2 pi r to the 4 over 4, which works out to be pi r to the 4 over 2. I've got a hollow shaft, which you sometimes do. You take pi times the outer radius to the 4 minus the inner radius to the 4 over 2. Okay, so those are the formulas for moment of inertia. They're on the back of your formula sheet, as are these other two formulas that we developed. Tau max is TR over I, and phi is TL over IG. Okay, to apply these formulas here, let's say we've got this hollow shaft, and we want to find the maximum shear stress and the twist angle in it. What we would do is first find moment of inertia. That's pi over 2, the outer radius to the 4 minus the inner radius to the 4. Just remember to work with the radii there. Usually you're given the diameters for a shaft, so you work with the radii instead. And that works out to be 3.94 times 10 to the minus 6 meters to the 4. When you're in the metric system, these moment of inertias are normally quite small. Okay, so we want to find the shear stress in this shaft, and also the twist at the end of the shaft of B with respect to A, which I've got dimensioned right there. Okay, there's the twist angle. All right, and we just apply the basic formulas. The shear stress is TR over I. Plug in T, R, and I, and we get 213 times 10 to the 6 newtons per meter squared, 2.13 megapascals. Here's the basic angle formula, TL over IG. We got all the values, plug them in. The torsion's 210. The length of the shaft is 1.4 meters. There's the moment of inertia, and here's the G value, which is given right there. Run the numbers, you get 0.0207 radians. That's the output of this formula. It comes out in radians. We can convert it into degrees. It's 1.19 degrees. Okay. Now a little bit more advanced problem here. Let's say we've got two constraints on the shaft. For this shaft here, we can't exceed 160 megapascals of shear stress, and the angle of twist cannot exceed 2.5 degrees. Convert the angle of twist into radians first by multiplying it by pi over 180. Calculate the moment of inertia by taking I as pi over 2r to the 4. R would be 0.06 meters there. So there's the moment of inertia, 20.4 times 10 to the minus 6 meters to the 4. Okay, now we've got our two basic formulas here. The shear formula, tau is TR over I. Solve it for T. It's tau I over R. Okay. We're doing this because we know the shear stress. We want to solve for what torsion would be required to cause the maximum allowable shear stress. So the maximum allowable shear stress is 160 times 10 to the 6 newtons per meter squared. I is 20.4 times 10 to the minus 6 meters to the 4, and R is 0.06. So when we work that through the formula, we get 54,287 newton meters. That's the torsion that would cause a shear stress of 160 megapascals. We also have the angle of twist is TL over IG. So back solve that for the torsion. It's the angle phi in radians. Remember, that has to be in radians. Times I times G over L. Plug in the values. We get this. 0.0436 radians times 20.4 times 10 to the minus 6 meters to the 4 times 60 times 10 to the 9 newtons per meter squared divided by the 2 meter length. That gets us a torsion of 26,600 Newton meters. So we get two different torsions for these two different limiting values. If our shear can't exceed 160 times 10 to the 6, we can apply a torsion of 54,287 Newton meters. If our angle can't exceed a twist at the end of the shaft there of 0.0436 radians, we get a torsion of 26,600 Newton meters. So the maximum allowable torsion is the lesser of the two, because if we exceed 26,600 Newton meters, we'll have too much twist in the shaft. Okay. So there's a little bit of an introduction to torsion.